Okay, welcome everyone. Let me bring up my slides. Okay, everyone seeing the slides?
Yes.
All right. Just the usual reminders about how you can join us. And if you want, take a snapshot. Different ways to work with us and all sorts of research threads we're personally working on in the Institute. In some cases, also the Corp, Centaur AI Corporation, our sister org, and also for those interested in systems work, programming languages work, there's this project. And presenters, brave presenters, or people just interested in these works, or others, and hiring, startups, donations, volunteers also welcome on helping us run events, Discord, discussions, or anything else you want to suggest. All right, and we're using the 1 hour format these days. And if the speaker has time, ideally can jump on Discord afterward to answer any remaining questions. And yesterday, the summer school was 100 days away. So it's coming up. We'll be providing more info soon, but save the date. You can go here to sign up at this link. It's a better way to save the date because it'll remind you. All right, and without further ado, Florentina. So, and this topic, just a little bit big picture, we try to cover in our curation, among other things, all different styles of neuro-symbolic, meaning ways that neuro interacts with symbolic. We ourselves work on multiple different versions of how that interaction works. So this is a kind that I'd like everyone to see. And we're fortunate to have Florentina speak with us today. And speaking from Austria. So again, reminder, this is global. So everyone from around the world, welcome, and our audiences all over the world. Okay, and you can see the papers she's going to cover here at these links, and we can send these out if people want, and then find out more about her work at her website. Okay, and we can take comments and questions, as always, from multiple sources you can watch from. And next week, NeurIPS, of course, is probably the biggest conference in AI as far as sheer mass. So a lot of people will be submitting. So in observation of that, we'll take a intermission next week. No talk next week. All right. And with that, let me hand it to our speaker.
Hello, I'm happy to be here. Can you already see my slides? Great, perfect. All right. Yeah, my talk will be about enhancing constraint programming with LLM-generated streamliners. Yeah, I'm Florentina. I'm a PhD student at TU Wien in Austria. Yeah, and now I present my work. So let's start with a recap of what constraint programming is. So constraint programming is a programming paradigm where you have declarative constraints to model decision and optimization problems. And there are many applications of constraint programming, for example, scheduling, routing, or planning. And of course, you can also model NP-hard problems. But the quality of the constraint programming encoding directly impacts the solving performance. And here I brought you an example of such an CP encoding. This is the n queens problem. So this problem is about placing n queens on a chessboard of size n times n, such that no two queens threaten each other. So yeah, we have n as a given integer, and we say there is an array where we fix which queen is in which row, and we also have to get sure that no two queens are in the same row, and we have another constraint so that no two queens are on the same diagonal. And as you can see here, this is an example of such a solution. Okay, so this is a constraint programming encoding. And now we have a look at so-called streamliners, because we can use streamliners to make such encodings more efficient. Streamliners are introduced in 2004 by Gomez and Salman, and these are basically additional constraints that narrow the search space. And they have the potential to significantly reduce the search effort. There are different types of these constraints. For example, redundant constraints. These are constraints that are basically implied by other constraints that are already there. Then there are symmetry breaking constraints. These exclude other symmetric solutions. So we can have an example here. If we add this symmetry breaking constraint, it says that the queen in the first column has to be in one of the upper rows. And on the left chessboard, here we have an solution for the general problem, but here, as you can see, the first queen is in the lowest row, but we can simply turn the chessboard and we will have a solution that also validates the additional constraint. And for this constraint, when there is a solution for the original problem, then there's always also a solution for this new model with the additional symmetry breaking constraint. That's in the definition of symmetry breaking constraints. There are also dominance breaking constraints and unsound constraints. Yeah, and unsound constraints are also very important here for our streamliners. Unsound constraints, they don't guarantee that every instance has a valid solution. So here's an example. We say that the queen in the first column has to be in the first row. And for n equals 5, there still exists a solution, and maybe the solver is even able to find this solution quicker than without this additional constraint. However, when we look at the instance with n equals 4, this would have a solution without this additional unsound constraint, but by adding this constraint, we cannot find a valid solution anymore. Yeah, so these are unsound constraints. There have been many successful applications of these streamliners, as you can see here with these paper examples. And yeah, in the past, these streamliners were mainly crafted by human experts. However, these needed a lot of manual effort and expert knowledge. There were also attempts that tried out to generate streamliners through exhaustive offline testing. However, these attempts could take multiple CPU days until they found a solution. So what we tried in our work was to use LLMs to generate streamliners. LLMs have multiple advantages. For example, they have some kind of creativity and intuition. They work automatically. No domain-specific knowledge is needed, and they are quite fast. So one LLM call takes only a few seconds. Of course, they also bring some challenges. So LLMs hallucinate, and they can produce errors or these unsound constraints. And this is why we designed our StreamLLM approach, where we use LLMs to generate streamliners automatically. And we have this real-time use case scenario where a user, on the one hand, just gives the CP encoding to a solver, and the solver starts solving the problem. And on the other hand, the user first gives the encoding to our approach. Then we find additional streamliners, and afterwards we run the streamlined encoding. And yeah, in some cases, our real-time approach worked better than just starting the original. So how is it working? We have some small training instances, about 15 instances that take less than 10 seconds to solve. And first, we start by finding the baseline. This means that we run these training instances on the unstreamlined original model that we know the original runtimes. And then we ask the LLM to give us 5 streamliners. We evaluate the streamliners. So we add the streamliners to the original encoding and run it on the training instances. And then we compare the running time of the streamlined encodings with the running time of the original encoding. And we store the streamliners that outperform the original encoding on the training instances. And this step is important because here we can also see whether the LLM produced streamliners with errors, for example, or whether the LLM produced streamliners that don't give us any improvement on the training instances. And we have this iterational loop. We do this for 10 minutes. And afterwards, we return 3 best streamliners. We return 3 of these streamliners because so that we can compare different streamliners. And also, we run the original model in parallel with the 3 best streamliners because, as I said, some of the streamliners might be unsound. And when we run the original model in parallel to them, then we can, in case all the generated streamliners are unsound, then we still have the solution from the original encoding. So this was the static approach. We also had an adaptive approach where we tested whether it's helpful when we run the streamliners, when we test the streamliners and then give the LLM a feedback of how well the streamliners performed. In the first step, we just asked the LLM for any streamliners, and then there were 2 iterations where we gave feedback and then start over again. Because we did not want to just give feedback to the given streamliners all the time, but we wanted to start over every 3rd iteration so that the LLM can try out new ideas. Okay, the LLM got a system prompt as input, and the mini-sync encoding of the original encoding. And in the system prompt, we gave the objective that it has to analyze the code and suggest streamliners. Then we had a chain of thought. So we gave steps that the LLM should do. So analyze the content, generate additional constraints, return in a JSON format, and so on. And also some compliance rules that told more about the format and that it should not contain errors and stuff like that. We conducted our experiments on 3 decision problems, namely the balanced incomplete block design, the car sequencing, the social golfers, vessel loading, black hole, carpet cutting, and hypergraph coloring. And for the hypergraph coloring problem, there was, to the best of our knowledge, no constraint programming model previously available. We tried to have such a new problem so that we can ensure that the results don't only depend on that the LLM is copying, pasting stuff that it already had in its training data. Yeah, for each of the problems, we had 15 training instances that took less than 10 seconds to solve. And we had at least 50 test instances per problem. And we tested it on 2 LLMs, namely GPT-4o and Claude 3.5 Sonnet. We tried out the static and the adaptive approach, and we had 2 runs to see the differences in the LLM answers. And then we reported the saved time. So what do I mean with saved time? Here I have a short example for you. Let's say that we have 3 instances, and the first instance took 50 minutes, the second instance took 30 minutes, and the third instance took 60 minutes in the original encoding. Then we have an overall running time of 140 minutes. And now we have now our approach run. We got the 3 best streamliners, namely the purple, the green, and the orange one in this case. And let's say that the green green streamlined model solved the first instance within 40 minutes. Then we can stop running all the other instances. Then for the second instance, again, we run all these 4 encodings at the same time. In this case, the original model found the solution after 30 minutes, and then we can also stop the other encodings. And then for the third instance, let's say that the orange streamliner found a solution within 20 minutes. So we report that time and can stop the other encodings. So overall, here we have 90 minutes. And so in this case, we would report 45% safe time. Okay, let's come to the results of the first experiment. Here we can see the different approaches, the adaptive and the static approach, as well as Claude and GPT. And the safe time is reported. So the higher the bar is, the better. And for each bar, we also have this black line, which like the lower of the black line is the result of one of the runs, and then the upper end is the result of the second run, and the height of the bar is exactly in the middle of the black line. And yeah, for most of the runs, we had quite similar results for the first and the second run, but there are also some cases where the first and second run had some differences. Yeah, so the results are quite impressive, especially, for example, here for the car sequencing problem. Here we got streamliners that led to 98% of safe time. So in other words, you can imagine that with the original encoding, the instance took maybe 1.5 hours to solve. And then with the streamlined encoding, it was solved in less than 1 second. So here we were quite impressed of how well this approach worked and how efficient streamliners are. Yeah, we can also see that Claude was performing slightly better than GPT, but yeah, since LLMs are updating their models every few months, we cannot generalize that. But we could also see that the adaptive and the static approach worked approximately equally well. That might be because the feedback reduces the exploratory potential of the LLM. Yeah, but it was interesting to observe that the feedback was not really helping, but that just the LLM trying a new idea is as productive as giving feedback. Yeah, we could also see that the performance on the hypergraph coloring problem was also quite reasonable. And this says that the LLM is not just copying and pasting the streamliners that it knows, but it's also working for an existing, for a new problem. That was quite nice. Yeah, so for some problems, it was working really well. For others, like the BIBD problem, it was not working so well, but yeah, it was also interesting to see. So yeah, as I told you before, we also had this real-time scenario in our mind where the user starts the unstreamlined model at the same time with our approach, and then afterwards running the streamlined encoding. And here you can see that, as we expected, when the original runtime of the instance is below 20 minutes, then our approach is not helping so much because it already takes 10 minutes to generate a streamliner. But with longer running times, you can see that the performance and the save time is increasing pretty much. We assume that when we would have instances with even longer running times, then this effect might even be stronger. We also did some tests on disguised and obfuscated problems. So disguised in this context means that we rename the identifiers and add comments such that we express the semantics of a different problem while maintaining the same syntax. So for example, we had the social golfers problem. This is a problem which is about assigning golfers to groups. And so we have a variable about n groups and n per group, like how many golfers are in one group and stuff like that. And the disguised problem in this case was about animals that live in a habitat, and we have to assign animals to an habitat. Yeah, and we also added a comment about that. Yes. So, and then we also tried the obfuscated problems. This means that we renamed the identifiers to arbitrary names, like ID 21, and we removed all the comments. So yeah, we have the same problem as before, and we just renamed it to ID 5, ID 2, and so on, so that the LLM has no chance to grab the meaning of the story behind. Yeah, here you can see the results for that. Again, we have here the static and the adaptive approach. We compared Claude to GPT. And blue means the original encoding, pink is the disguised encoding, and yellow is the obfuscated encoding. And yeah, here you have the different problems at the top. And what you can mainly see is that the disguised problems are working equally well to the original problems, and that suggests that the LLM is not just copying and pasting the given streamliners for the given problems, but at least it can think of, yeah, this problem might be similar to this other problem. For the obfuscated problems, the performance was a bit worse, and this suggests that the LLM prefers a richer language to make sense of the problems. Okay. Then we also did an offline approach. This means that we had longer running times, and we ran our approach not just for 10 minutes, but for 4 hours. And we did not just had 15 training instances, but 35 training instances. And we tested in the same run, we randomly picked either GPT or Claude and picked a different LLM in each iteration, so that we can make use of the strength of both LLMs. And what we can see, so we tried this out for the black hole problem and for the carpet cutting problem, because these two problems performed medium well in the experience before. It would not have made sense to take a problem that already had 98% of saved time. So these two were performing medium well. And what you can see that after some time, the performance is getting better. And what is also interesting to see is that there is a strong correlation between the training and the test, between the results on the training and the test instances. So yeah, we tried 2 runs, and the blue one here is the first run, and with the dots, this is the results on the test instances, and with the crosses here, this is the performance on the training instances. And you can see that there is quite some correlation. And also you can see after about 2 hours, it was already performing quite well. And and overall, it could reach a safe time of over 90%. So yeah, in this case, we showed that longer running time can lead to even better results. Yeah, then we also did a small analysis of the Streamliners. Here at the contribution, we so for each problem, we picked the 3 best performing Streamliners for 1 run, and the contribution means how, like in the for each instance, how, like, which of the Streamliners or the original model was performing the best. So for example, here for the black hole problem, the original encoding was performing best in 11% of the instances. Streamliner 1 was performing best on 60% of the instances, and Streamliner 2 was performing best on 26% of the instances, where the Streamliner 3 was not so good compared to the others. What is interesting to see here is that for the carpet cutting problem and for the social golfers problem, the car sequencing and the hypergraph coloring problem, the original encoding had 0% contribution. That means that for each instance, there was at least 1 streamlined encoding that performed better than the original encoding, which is very nice. And what we can also see is here, for example, for the hypergraph coloring, that there was one streamlined encoding that had 98% of contribution. So there was one streamliner that performed really, really well and outperformed the other streamliners and the original encoding by far. For other encodings, for example, for the vessel loading problem, we can see that the performance is approximately evenly distributed between the original and the free streamlined encodings. Yeah, and what's also interesting to see is that some of the streamliners did not produce any unsound instances, but others did. Yeah, and it's also for some cases it was really interesting to see that, for example, there might be a streamliner that solves 80% of the instances very well, but for 20% of the instances it's not working. However, if you run it in parallel with the original encoding, then it might still be worth to include this unsound streamliner because it's great performance on some of the instances. So we found that it's still worth including these unsound streamliners because they can have great potential on some of the instances. Yeah, we also did an analysis of the type of streamliners. Yeah, found out that yeah, some of them are unsound streamliners, but we also had some redundant constraints indicated by the I, two symmetry breaking constraints indicated by the S, and the use means that we were not sure and we had no formal proof of which type it is. Okay. All right. Yeah, let's come to a conclusion. So we could show that the StreamLLM approach had significant improvements in solving times. And this was even the case in real-time scenarios where we first computed the streamliners and then run them. And yeah, we also showed that unsound streamliners can have a high potential. There are some ways of follow-up work. For example, one could use fine-tuned LLMs that might perform even better or are quicker. Or what would also be very interesting is to develop an LLM-supported formal verification for streamliner soundness. So it would be great if we could somehow mathematically prove that these streamliners are sound, because then we would not have to run them in parallel to the original encoding. I also did some research on optimization problems with the same approach. There you don't compare the running times of the streamlined encodings, but you compare when you have a given timeout whether the streamlined encodings achieve better objective values. If you're interested in that, I also have a paper there which was accepted to the Constraint Programming Conference last year. Okay, I think I'm done with my talk. Yeah, if you are still interested in some details and the implementation, feel free to read the full paper. Yeah, to sum it up, the key takeaway is that LLMs can efficiently generate streamliners that significantly reduce solving time. Yeah, with that, thank you for listening. I hope it was interesting.
All right, very nice. Thank you, Florentina. Questions, Olga?
Yes, we have a couple of questions. First one is, what are the main differences between a streamliner and a heuristic in the classical sense?
Between a streamliner and a heuristic?
Yeah.
It's a good question. I mean, so streamliner in our sense is one additional constraint. So I'm not sure what. Yeah. So maybe it has some similarities, but I would say it depends on the use case. So in this scenario with the constraint programming, we call it streamliners and add just these few constraints. I would say heuristics can also be used with other algorithms. If you, for example, write an algorithm in Python, then you can also use an heuristic. But I guess it has some similarities, yeah.
I would say normally when we talk about heuristics, we mean something that is built into the search or optimization itself that helps guide it, in a ideally to be more efficient. But in this case, it's like a pre-step. I mean, similar to preconditioning in linear algebra, where you're trying to massage the problem before you feed it to the optimizer. So, but in that massaging, they're effectively heuristics for, because the massaging could be seen itself as a kind of optimization problem. So I would say it's like heuristics for the pre-optimization problem.
Yeah, well, thank you for the explanation.
Okay, another question we have, are there characteristics of the problem which could help get some kind of classification of fine-tuned problems and corresponding classes of problems? Should I read it?
Yes, please.
Are there characteristics of the problems which could help get some kind of classification of fine-tuned problems and corresponding classes of problems? Do you understand the question?
So are there characteristics of problems that help to find classification for the problems?
Of fine-tuned problems and corresponding classes of problems. I see probably the person is typing maybe some clarification on the question.
I have a guess at what that means, but let's see. I think that may be asking, once you see you've seen these behaviors over many problems, can you start to classify them as in a taxonomy or groupings of types of problems, maybe based on high-level characteristics of the problems that point to different behaviors under streamliners.
So like, for example, that for some problems, some types of streamliners may work better than for other problems.
Something like that, yeah.
Something like that?
I think maybe, or I'll rephrase it to a related question, perhaps. Let's see if the asker has a clarification.
But yeah, I would say that when there are similar types of problems, then it's also likely that the good working streamliners look similar.
There's that, but also, like, if you have a problem, a particular problem you're wanting to apply a streamliner to, what can you say about what will happen based on the characteristics of the problem?
Yeah, but I think that's exactly the thing why we use LLMs, so that we don't have to think as human expert what will happen. Of course, when you really know how the problem works and you have understanding of it, and you can manually add a streamliner. Yeah, but in this case, that's the reason why you want to use LLMs, to have it automatically.
Fair. But based on what you saw, did you see some kinds of problems are working better?
Yeah, so also I saw that in the results of the experiments that some were working better than others. But for me, it's hard to say what exactly the differences are. I mean, to some extent, maybe it also depends on how famous this problem is in literature and how much the LLM has learned from it. Maybe that might be a reason for that. Maybe there are some, it can definitely be that there are some type of problems where there are better symmetry breaking constraints, for example, existing than for others. Yeah, so there's definitely some differences.
Mm-hmm.
And also one thing that I noted is our approach works better when, oh no, sorry, that was a thing for the optimization problems. But yeah, so for example, when we look at the optimization problems, there are problems where it is hard to find at least one solution, and it takes forever to find the first solution. And there are other instances or other problems where it's easy to find one solution, and then it slightly improves, the objective value improves the longer you run it, and you can see the small improvements. And so, for example, for these optimization problems, our approach is also working much better, because then the LLM can already test with training instances these small improvements. Yeah.
Mm-hmm. Thank you. And there are follow-up questions, I believe, from the same person. How about meta evaluation? And in parentheses, do you know the classic heuristic of Doug Lennart? I'm sorry if I'm not pronouncing that correctly. I have not heard about this. Once again, how about meta evaluation? Do you know the classic heuristic of Doug Lennart?
No, I don't know that.
Okay. Well, what makes types similar? It's probably follow-up from the previous question. And yeah, there is a couple of questions, like similar syntax semantic of the grammar, for instance.
Mm-hmm. Yeah, or whether I mean, problems can have many forms. So, for example, one way a model can be, encoding can be modeled, is that you have an array where you assign something to some value, and then you have this assign array. Some other problems might look for a certain value or try to optimize something. So there are certain structures, and yeah, I think when they have certain, like when they're using similar approaches to model it, then also maybe the streamliners might be similar.
Mm-hmm. Thank you. These are all the questions from the audience for now, but I have a couple of questions myself while we are waiting for more questions potentially. So, Florentina, you mentioned that like one of the steps in your analysis was Streamliners evaluation. I'm curious, how is it done? Is it manual? Is it automatical? If so, how you do it? Like how, like once there are some, let's call them candidates, maybe streamline candidates, how do you decide which ones are good and which ones are not good? And maybe related questions, not sure if it's separate or related question, like how you, what do you do with hallucinations? Like how do you identify if maybe this streamliner was some result of hallucination or not?
Mm-hmm. Yeah, so how do we do the evaluation? We have for each problem 15 training instances that only take less than 10 seconds. And then we ask the LLM to give us some streamliners, and we still have the original encoding. And then we plug in the streamliner into the original encoding, and then we run the streamlined LLM on the 15 training instances and store the running times. At this point, we can already recognize some hallucinations. So, for example, if we get, I don't know, a happy birthday instead of a streamliner, then the code will already recognize that this is not fitting. And also if we get the wrong format and stuff, so we can already filter out these things. Also, if we get some syntax errors, we can already filter them out at this step. We also filter out streamliners where no training instance could be improved. And if there is at least one instance that performed better with the streamlined encoding, then we save the streamliner together with the running times for each instance. And then after the 10 minutes, we compare all the streamliners that we found that improve at least one training instance, and then we pick the 3 best.
What do you mean by best? How do you identify best ones?
Yeah, so in this case, we look at we build all the possible triples of 3 streamliners, and we look on if we would run them in parallel on the training instances and always take the best streamlined encoding for each instance, which triple of streamliners is the best from the whole pool of streamliners.
Oh,
Was it clear?
Yeah, so you consider all possible triples of streamliners.
Yes, yes.
I see. Okay, and actually, you touched on another thing that I had a question on, like about these 50 train instances, small ones. How do you create those? Is it manual, or like if you have like a bigger problem, how do you create these small training instances?
So it depends on the problem. So for example, the social golfer problem has as input 2 variables. And so we just create many instances by just like randomly picking values for these 2 variables. And then we run them to see whether they fit into our time window. So for problems where there are just a few input variables, this is easy created automatically and then tested. And for other problems where the input might be an array, for example, or multiple values, we used another pipeline called AutoIG. It's described a bit more in detail in the paper. But yeah, it's also a framework which creates different possible instances and then runs them to test whether they are within the given time bound. Yeah, but it was some effort to create the test instances and the training instances. At first we thought maybe it would be enough to look at existing benchmark instances, but the problem here was that not all of them were within the time bounds that we wanted to have. And so that we have the same time bounds for each of the problems, it was easier to create the instances ourselves.
Okay, thank you. We received one more question from audience. Given you play Go with streamliners, would some of them be combinable?
So for the social golfer problem?
It just asked about playing Go.
So I guess it's about the social golfer problem. And so there are already famous symmetry breaking constraints. And some of them are possible to combine. So for example, for the social golfers problem, we have this array where we assign for each golfer in which week they are in which group. And one very common symmetry breaking constraints is that we say the first golfer is in the first group, the second golfer is in the second group, the third golfer is in the third group, and so on. And then, for example, when we have 3 groups, then we say that the third golfer, of course, is not in the fourth group because it's not existing, but is in the first group again. And then we already assign all the golfers to their groups in the first week. This is one common symmetry breaking constraint. And another common symmetry breaking constraint is to always assign the first golfer to the first group. And these 2 symmetry breaking constraints can be combined. However, there are also cases where 2 individual symmetry breaking constraints are working, but that cannot be combined.
Yeah, I'm really sorry, Florentina. It was meant Go like in AlphaGo or like Japanese Go game. It's not like golf. It's like this, like in AlphaGo, you know?
So wait, then the question was, in AlphaGo, how
could you combine some streamliners?
Yeah, since I'm not exactly knowing how AlphaGo is working in the background, I'm not sure.
Okay, thank you. The next question we have you tried some open source LLM models behavior?
In this case, not. In general, for some other experiments, I also tried some open source models. In general, I would say that the performance of the open source model is slightly worse. However, since models are improving every some months or every some weeks, I would assume that models, that open source models in a few months are already working as well as paid models right now. So if it's not important to have the very best performance, it's totally fine to also try it out with open source models. I assume that this approach should also work with open source models, yeah. But I have not rigid experiments on that.
Thank you very much. These are all the questions from the audience. Alex, do you have any comments or questions from your end?
Yeah, just a few. So first, I think just a comment overall on this kind of thing and why I think it's good to look at. You know, it's sort of related to this popular thing that's popular now, which tool use by LLMs, calling out the things they're not inherently good at, you know, sub-solvers, and like doing math and stuff like that. Particularly things that are symbolic make sense. And this is a particularly complicated kind of symbolic thing. So it's exactly where you'd want to do tool use, but it's going a step further, which is having the LLM massage it first too, before calling it out. So you could look at it that way. And so I think things we can learn here might be illustrated for this general pattern that many people want to do in industry, where the assumption is the core kind of is the LLM and other things will be called out. So this disguise, one question I have, I really like that you did these experiments around disguise and obfuscation. I think more people should really do that because, and to me, what you showed is that although in one, on disguise, you said roughly, sometimes it's better, sometimes worse, but roughly, you know, you could say it evens out. But But on a per, it's still interesting, I think, that on a per instance basis, you really don't know. It might actually make it better, it might make it worse, and kind of by a lot, actually, right? Potentially. So, so there's a lot of variability, even when the semantics are identical, right? If essentially the syntax, the words that are used, change the behavior of the LM quite a lot. So I think that's a really important point. It's really not stable in the semantics. Like it's highly sort of distractible, you could say, by the actual surface form. So, and then of course in the obfuscation, you're really trying to distract it, and and there you see drop in performance. But I think that's one kind of takeaway that is important here in your results. Any comments on that?
Yeah, definitely. First of all, our initial thought why we wanted to try to disguise and obfuscate it was that we can check that the LLM is not just copy and pasting the stuff from the internet. But as you said, it's also very interesting that for some problems, the disguised version might work better. And we also thought of maybe it could make sense in our approach that we run the same problem with different disguised versions to get an even better result. We thought maybe that could also be an interesting future work. And also one could even use another LLM to automatically disguise the problem so that the whole approach is still automatically. But yeah, it definitely makes sense for LLMs to write things in a different way, and you never know what comes out, and maybe with writing it in a different way, the results are even better.
So I think this is related to one of the earlier questions from the audience, like which I'll sort of translate to: when can you know the LLM will, how well it'll work? But if you, based on the characteristics of the problem, but in particular, because it can make it worse and possibly even unsound, like not solvable, then you kind of want to know. I think you're in your experimental setup right now. You're basically not too worried about it because there's short problems. You just try it basically, and you just see is it better or is it But I think it would matter for really large problems, right? Because then the whole point is you don't want to take the solver to take a day. You want to see if you can improve that, but you also don't want to run 10 experiments with LLMs that each could take a day, or
Of course, yeah.
slower, or possibly even not solve. So I think it might be important to kind of develop a predictive model, at least, or something that tells you when gives you a higher probability of knowing it's gonna help.
Yes, that definitely would be right. I mean, we had our training instances, and often the performance of the with the training instances was similar to the performance on the test instances. So if you really have a big problem that takes multiple days to solve, maybe it makes sense to run some streamlined models on the smaller training instances, then you can already guess whether it's improving the model or not.
Last question, real quick. I think you open the talk by saying if you don't use LLMs, you basically have humans making the streamliner, or maybe have, I think it was a sampling approach or something.
Mm-hmm.
That could also be costly. Do it, but even if those are costly, they could provide better streamliners. Or at least that seems like it would be worth an experiment to see, if you invoke the cost of a human doing it, then at least does the human do better than the LLM? And same with the other automated approach. It might be expensive, but it might actually do better than the LLM.
Maybe, yes.
Yeah, who knows? But what do you think of that?
Yeah, I mean, I'm sure that when there is a human expert who has knowledge in this area, knows about the problem, sits down for a day, then I'm optimistic that this person will find better streamliners. And what's also very important is that this person can verify whether these streamliners are unsound or not. That's a big advantage. So, of course, if you have the person, the knowledge, and the time to generate streamliners by yourself, please do it. But yeah, our approach is rather an alternative for if you don't have the knowledge or don't have the time, then I would say it's also a good thing that we have our approach, even though the other approaches might perform a bit better.
All right, very good. I think we're at time, but thanks so much, Martina. And
I'm happy to hear.
Yeah. Glad you came. Everyone, check out her work and the papers, of course, but also her other work. And thanks again, and take care, everyone. We'll see you a week from next.
Bye.